In this presentation, I am going to explain the closed loop control of boost converter using one cycle control OCC. Another presentation, I have already explained the one cycle control for a buck converter. In that one, the basic concept of one cycle control is explained. And you please listen to that presentation before coming to this presentation. Now coming to the basic working of a boost converter. And boost converter, the topology circuit diagram is shown here. At the input side, there's an inductor, switch is there, a diode is there, a filter capacitor is there, this is the load is there, input voltage equal to VD, and the average output voltage equal to V0. Now let us derive the equation, average output voltage divided by the input voltage, that will be deriving. That can be derived by considering first what is the voltage across the inductor when switch is on. When switch is on, the corresponding equivalent circuit is this one. Therefore, here the input voltage VD will be coming across the inductance, or the voltage across the inductance is equal to plus VD, same as this one, plus VD here. And when switch is off here, then the equivalent circuit is this one, because that will be whatever the energy stored in the inductor will be transferred to the load, and here the equivalent circuit is as shown here. And in this case, again we are applying the Kirchhoff's voltage law. You can find out what is the voltage across the inductor. The voltage across the inductor equal to the input voltage VD minus the output voltage, average output voltage V0, or VD minus V0 is the VL, VD minus V0, or that can be written as minus of V0 minus VD. Therefore, this is the voltage across the inductor when switch is off, and this is the voltage across the inductor when switch is on. Therefore, during the on position, since the voltage across the inductor is positive, the current through the inductor is building up with a positive slope. And when switch is off, the voltage across the inductor is negative. That is why the current through the inductor is decaying with a negative slope. Therefore, this is the current through the inductor, and this is the voltage across the inductor. Same thing shown here. This is the voltage across the inductor when switch is on, which is equal to the voltage VD, and when switch is off, the voltage is equal to VD minus V0, or minus of V0 minus VD. Now, as per the volt second balance concept, the average voltage across the inductor over one switching period should be equal to 0, meaning that the product of volt and second is nothing but the area. The positive area should be equal to negative area, or net area after one switching period should be equal to 0. Otherwise, the flux will be, the change in flux will be occurring, or flux linkage happens, and that will be finally the core gets saturated after a few switching cycles. Therefore, in order to avoid that one, the volt second balance should be obeyed, or this positive area should be equal to the negative area. Applying that one here, we can see that one VD is the voltage magnitude, and this area means voltage VD, and this is the time is equal to the on period. For VD into T on, then this is equal to minus of V0 minus VD, minus of V0 minus VD into the off period. Off period is nothing but the time period Ts minus T on. That should be equal to 0. The net area should be equal to 0. Equating that one, and we'll be getting here VD into T on minus V0 into Ts plus V0 into T on plus VD into Ts minus VD into T on. That should be equal to 0. Or V0 into Ts minus T on equal to VD into Ts, or V0 divided by VD equal to Ts divided by Ts minus T on. Now dividing numerator and denominator by Ts, we'll be getting V0 by VD equal to 1 by 1 minus T on divided by Ts, which is nothing but D, duty cycle, T on divided by Ts. Therefore, the average output voltage V0 divided by the input voltage equal to 1 by 1 minus D, where D equal to D is called the duty cycle, which is equal to T on divided by Ts. Therefore, by changing the duty cycle D, we can vary the average output voltage. For example, if we are keeping D as equal to say 0.5, 1 by 1 minus 0.5 decimal 2, or output voltage is equal to 2 times the input voltage. Therefore, output voltage can be more than the input voltage. That is why it is called a boost converter. Now let us see the closed loop control of a boost converter using a PI controller. Therefore, this is the Simulink model of the boost converter. That is a voltage source, inductance, there's a switch is there, diode is there, and capacitance, a load is there. Therefore, this is the power circuit. And let us see the control circuit, or in that case, in a PI controller based control circuit here, output voltage is sensed and that is compared with the reference. That is sensed and the reference is given, that is compared. And the error is given to a PI controller, and the PI controller is compared with a sawtooth waveform, and that output of this one comparator is given to the switching signal to the this switching device, maybe the MOSFET. Therefore, this is the closed loop control of a of a boost converter using a PI controller, in which we are seeing as the input voltage is suddenly changing. The input voltage is changing from 5 volt to 7 volt, and what the reference voltage we have kept is 12 volt. Therefore, what we want to get the output voltage equal to 12 volts. That's the reference voltage, and the input voltage perturbation is given from 5 volt to 7 volt. Let us see the response or the in the coming slide. Now continuing the closed loop control of boost converter using PI controller. Now as we have already seen the Simulink model diagram here, and here the reference voltage is given as 12 volts and the input voltage perturbation is given from 5 volt to 7 volt. Now let us see what is the output voltage waveform as such. For here the input voltage is suddenly changing at this instant from 5 volt to 7 volt, and this is the response of, that is the voltage at the output side. What we have kept is the 12 volts. For the 12 volts is there. For suddenly when the input is perturbing or the changing from 5 volt to 7 volt, that there's a overshoot is happening, and after some time settling time, that is finally settling to the reference voltage or 12 volts is getting. Therefore, this is the PI, the closed loop control of boost converter using PI controller response that here, that is the and this is the input voltage change and this is the output voltage. In the coming slides, we are going to see the one cycle control, how this closed loop control of boost converter can be realized using one cycle control. What is the general procedure to implement the one cycle control? And we'll be comparing with the response of PI controller. The general procedure to implement the one cycle control, first thing is that first we write the corresponding the equation, output voltage divided by input voltage relation 1 by 1 minus d. This is for a boost converter, V0 by Vd equal to 1 by 1 minus d. Or first the voltage gain equation is written, V0 by Vd equal to 1 by 1 minus d for a boost converter. First step is that. Second step is that since we want to have an output voltage same as the reference voltage, we'll be replacing the V0 by V reference. Therefore, this equation now it becomes V reference divided by Vd equal to 1 by 1 minus d. For a boost converter, this equation now reduces to V reference divided by Vd equal to 1 by 1 minus d. Or that indicates that V reference into 1 minus d equal to Vd, or V reference minus Vd equal to d times V reference. V reference minus Vd equal to d times V reference. That is derived from this equation. Third step is that same thing here, combining the term having the d and not having. In this case, same thing has done here. This is the terms which does not have the d, and this is the term which is having the d. That is separated like this one. And the fourth step is that this d is being replaced by 1 by ts integral 0 to t on whatever that that into dt. Or in boost converter, the corresponding equation, this equation will be reducing like this one, V reference minus Vd equal to d times V reference, which is equal to 1 by ts integral 0 to on period t on whatever this one, that this will be coming here into V reference into dt. Therefore, this is the in boost converter, this is the relation now we have to implement. Now continuing the general procedure to implement the one cycle control. This is as far as for a boost converter, we have seen that one, and here this is a power circuit and this is a one cycle control circuit. We'll see in details. And here as a fifth step is that the combined terms having d is given as an input to the resettable integrator. In this case, the term containing d, that's only the that's only VREF. That is reference voltage. Whatever we are going to get the output on, that is called the reference voltage. That is only the term which is along and with the d. Therefore, this term is given as an input to the resettable integrator. Therefore, here the reference voltage that is given as a that is given to the resettable integrator as an input to the resettable integrator. Of course, that is given to an inverting terminal of the integrator. In boost converter, V reference is given as an input to the resettable integrator, because here the term along with D is equal to VREF or reference voltage, that is given as an input to the integrator, inverting terminal of the integrator. And this integrator output is given to the negative terminal of the comparator. For the integrator output, actually this is a multiplication required. Because the time constant of the integrator should be equal to the time period of the clock period. We'll be seeing that one. Therefore, we have to do a multiplication that will be clear in the coming slides. Therefore, the multiplication is required. That is, combinedly, this is the integrator plus a multiplier is required. And after that one, that signal is given as the, that is the boost converter. V reference is given as this integrator output is given as a the positive terminal to the comparator. The comparator having a positive terminal and negative terminal. And this output of the integrator after multiplication, that is given as an input to the positive terminal of the comparator. That's given the positive terminal of the comparator. And the combined term that does not have D, for example, in this case, if you see, look into the boost converter, this is the term that does not have D, that V reference minus VD. That is given to the negative terminal of the comparator. For in this case, we can see that one, V reference minus VD. V reference is this one, and that is VD means input voltage. That is subtracted from this one, and that is given as the negative input to the comparator. That is given a negative terminal to the comparator. In boost converter, V reference minus VD is given to the negative terminal of the comparator. Now continuing the procedure to implement OCC, the 8th step is that output of the comparator is given. We have seen what is the input to the comparator plus point, that is output of the resettable integrator, and this negative is equal to the term that does not have the D, which is equal to V reference minus VD. That is given as an input here. That is, of course, here it is, that is given as an input to this one. And the output of the comparator, that is given as to, this is output of comparator is given to the reset pin. It is equal to the reset pin of that one. It is given to the reset pin of the SR flip-flop. It is given as reset pin. And the clock signal is given to the set, that is, this is a clock signal that is given to the set terminal of the SR flip-flop. SR flip-flop. The clock, and then one thing is that the time period of the clock, that should be same as the time constant of the integrator. That should be satisfied. Time period of the clock should be same as the integrator time constant. And see, after that one, we have seen this is given to the R terminal of the SR flip-flop, and this is given to the set terminal of the SR flip-flop. And the Q output of this SR flip-flop, Q output, that is given to the switch. So the Q terminal of the SR flip-flop is given to the switch, and Q bar is given to reset pin of the resettable integrator after providing a delay. It is that is Q bar is given to a reset switch of the integrator. That is given to that one. So this is the way in which the one cycle control technique is being, or that is being implementing here. Now the input to the integrator, we have seen it is equal to, that is equal to the reference voltage, and here the reference voltage, of course, that is the corresponding the input to this one, that is the input to the input to the, this is given to positive terminal of the comparator, and to the negative terminal of the comparator, we have seen, as already we have seen, the negative, that's given by V reference minus VD. That is here the V reference voltage minus VD is given as the negative terminal of the comparator. So the output of this one is given to the reset pin, and Q is given as to the switch. Of course, the here to the set pin we are giving from the clock output is given the set pin, and Q bar is given to the reset pin of the this resettable integrator. Therefore, this is the way in which the OCC being implementing for a boost converter. Now we have already seen the boost converter diagram, or that is topology like that one. Already we have explained that one. The input side is inductor, is switch is there, across the load there's a filter capacitor is there. Everything I have explained that one. Now let us see the one cycle control of boost converter, how to be implemented. Already we have seen the voltage gain equation as V0 by VD equal to 1 by 1 minus T. In closed loop, output voltage should be equal to, normally what we want to, the method is that we'll be replacing the V0 by V reference, and as I already explained in the previous slides, V0 will be replacing the V reference, and then the equation become V reference divided by Vd into 1, Vd equal to 1 by 1 minus d, or we can see that one V0 equal to V0 equal to will be getting it, V0 which is equal to V reference, which is equal to Vd divided by 1 minus d. That is V0 which is equal to V reference, which is equal to Vd by 1 minus d. Therefore, from this equation, we will be getting what is that V reference minus Vd equal to V reference into d, or V reference minus Vd, that is equal to d is replaced by 1 by Ts, 1 by Ts integral 0 to t on V reference. Therefore, now how to implement we'll be seeing in the coming slides. Now this is the simulating model of a closed loop control of boost converter using one cycle control, in which this is the power circuit. This is the power circuit as such, and here this is the input voltage, and here we are giving a step input is given, because to have a perturbation at the input side, we are giving a step input at the input voltage source, and this is the inductance at the input side. There is a switch is there, and there is a diode, and the capacitor, filter capacitor is there, and a load resistance is there. Therefore, this is the power circuit. Now let us see what is one cycle control. That one cycle control, basically, as we have already seen in the previous slides, to the integrator we are giving what is that to the integrator, whatever the term that is coming along with d is given as the integrator. For V reference minus Vd equal to d reference, d into V reference. This is the equation. Therefore, whatever the term along with the d, that is given directly to the resettable integrator. Therefore, the reference signal is this one. That reference signal is given as 30 volts. That is given as one input to the resettable integrator. That is this one. And here, this one to the that resettable integrator output is after providing a gain that is given to the positive terminal of the comparator. Now, what is the gain of this one to be calculating that one? The time constant of the integrator should be same as the clock time period. And here the clock time period is we have to calculate what is the frequency is equal to 10 kilohertz. We have selected a clock frequency equal to 10 kilohertz. For the time period equal to 1 by 10 into 10 raised to 3, that is 1 by 10, or that will be getting 0.1 milliseconds. Therefore, that is why k equal to the multiplication factor, the k equal to that is equal to 1 by ts, or 1 by 0.1 millisecond, or that's equal to 10,000. For we are selecting the multiplication factor 10,000 here, and the output of that one, therefore totally this can be considered as total integrator, and that output can be given as the positive terminal of the comparator. That is being compared with the whatever this signal, that is which is equal to V reference minus Vd. V reference minus the input voltage that is taken as Vd, then take the difference of that one, that is given as the negative input of the comparator, and the output of the comparator is given to the reset pin of the SR flip-flop, and to the set pin we are giving the clock input that is set to 10 kilohertz. That is the clock input is given, and the output Q of the SR flip-flop is given to the switch, and Q bar is given to the resettable pin of that one, that is to the resettable pin with a delay 1 by Z. Therefore, here this is the simulating model of the one cycle control of a boost converter, in which the things to be remembered is that one input to the resettable integrator is which is equal to whatever the component along with the D, that is V reference here. Another input to the that is the comparator input, that is given by whatever the term that does not have D, or V reference minus Vd is taken as input to the negative input of the comparator. Therefore, this is the simulating model of a one cycle control based boost converter. This is the boost converter with the one cycle control input and output waveform. That is, input is suddenly changing, that is input is changing from 20 to 25 volts. Here 25 and the 25 volts it is suddenly changing, and the reference voltage equal to 30. The reference voltage equal to 30. You can see the output response here. This is the output of the output of the boost converter. You can see even though there is a transition at this instant like 20 to 25, that is not at all seeing at this one. So this is the output voltage response, and this is the input voltage variation or perturbation, this one, based on the one cycle control. Now let us compare the performance of one cycle control and the PI control that is used for a boost converter, closed loop control. For in this case, the input voltage is perturbing, or that is changing from 20 volts to 25 volts, as we have already seen. The input voltage is changing from 20 to 25 volts, let's say, and the reference voltage what we have selected is equal to 30 volts. And this is the output voltage waveform corresponding to the one cycle control OCC. And as already we have seen, this is the PI control. Based on the PI control, the output voltage waveform is this one. Now, if you compare this one, that is the input voltage with the voltage perturbation is shown here, A, and B is the output voltage using one cycle control, and C is the output voltage using PI controller. Now, if you compare with this one, you can see that one here, there's no even overshoot is absent here in one cycle control. Another point is that here the settling time, this much is the time to settle that one. Here, settling time is very, here that is, theoretically it is 1 milli, is very, very less as it. Here it is equal to 50 millisecond. Therefore, it is very fast response is there. I mean, whenever there is an input voltage perturbation, the output is not much changing, as well as the settling time is very, very less for the OCC, one cycle control, compared to the PI control. Therefore, that is the performance comparison between one cycle control and PI controller for a boost converter when input voltage perturbation is done. Now let us see the performance comparison of between OCC, one cycle control, and PI controller for a boost converter closed loop control, in which the reference voltage is changing from 40 volts to 30 volts. For example, this is the reference voltage. Until this one, the reference or required voltage equal to 40. Suddenly that is changing to the reference voltage is changing to 30. And here we can see that one reference voltage. This is the output voltage. Until this one, it will be getting the output voltage is here 40, and it is suddenly changing to 30. This is the response using the one cycle control method as the reference voltage changes, and this is the response corresponding to PI control methods. Therefore, if you compare the settling time, which one, this is equal to less than the OCC, less than for OCC compared to the PI controller. For PI controller, it is 25 milliseconds, the settling time. Here it is equal to 10 milliseconds. Therefore, this is the plot. First one shows the reference voltage change. Reference voltage is changing from 40 volts to 30 volts. And the second, B, is the output voltage change. That as the reference voltage changes, of course, the output voltage, the reference output voltage has to change. And this is corresponding to the OCC, and this is corresponding to PI controller. Therefore, comparing these two things, the settling time for the OCC one cycle control is less than the PI control method.